So today's talk would be outside of the main development of the other subject that I started yesterday. It's sort of an independent presentation about some recent, mostly just a review of some recent work by Smirnov and Zamolodchikov, based on some ongoing work with Stefano Negro and Zamolodchikov. I would not present many new results, just a few, but from a point of view that I think would be perhaps more clear. So we'll study some properties of the energy momentum tensor in 1+1 dimensions. So one axiom that we always require is that it's symmetric. The other thing that we require from the energy momentum tensor is that it's conserved. And if we'd like to study conformal field theories, we also require that the energy momentum tensor is traceless, but that would not be something that I would impose. We will not study conformal field theories. So we'll start from studying the two-point function in the vacuum on R2. So I'll be thinking Euclidean for the sake of simplicity. So we'll start from the two-point function in the vacuum, which I'll denote by this function g, which depends on these four indices, mu, nu, rho, sigma, and on the distance between the 2 points x and y. And the first small exercise, preparatory exercise that we'll do will be to try to see how many functions do you need to, how many independent functions are there in this beast. Okay, so we need to solve the conservation equation and make sure that the energy momentum tensor is symmetric. But in addition, there is also a requirement of Bose symmetry, that when you interchange the two energy momentum tensors, you get back you get back the same function. So how we first want to understand how many independent functions are there. How many independent functions? So the most convenient way I'm aware of solving this problem is to Fourier transform to a momentum space, because that constraint becomes algebraic. So we just Fourier transform this function. So this is x minus y. We Fourier transform to momentum space, and then we get some function of q, which we can denote with a twiddle. And now the constraint of conservation becomes algebraic and straightforward to solve. An important point here that will appear again very soon is that when we impose these constraints, we only impose them at separated points. Okay, so at coincident points, it might be that this is not satisfied. However, this is satisfied even at coincident points, but this may not be satisfied at coincident points. So this is for separated points. This will be important, as you'll see. So I'll start from something very basic, and then we'll get to the more interesting advanced things. So solving this algebraic constraint that allows for two different structures to exist, and they come with independent functions. So the first structure is q mu rho, q mu q rho minus q squared eta mu rho. And this is a small exercise that you can solve at home, just to make sure that indeed these are the only allowed two structures by these constraints. So rho. So this is the first structure, and this multiplies some unknown function f of q squared. And the second structure is a little bit simpler. It's q mu q nu minus q squared eta mu nu. And then q rho q sigma minus q squared eta rho sigma. And then some function g. And in general, quantum field theory, which may not be conformal, we don't know what these functions g and f are. They are not non-trivial functions, but these are the only two functions that you can write down. consistent with the various constraints. Okay, this has been known for, of course, for ages. And the new observation starts from the following cute technical fact. And then we'll try to understand this. We'll see what is the significance of this technical fact. So we'll study the following contraction of this function. So mu rho, mu sigma, g mu nu, rho sigma, q. So we'll study this funny combination just to see what we might get. And what I claim is true is that this gives exactly 0. This combination exactly is annihilated. So what is this combination? Let me just make a small parenthetical comment. So this combination that we just defined this basically, if you just write it in terms of the energy momentum tensor, and if you go to complex coordinates, z and z bar, then this is essentially like tzz, sorry, this is too small, tzz, tz bar, z bar. Sometimes people put a bar here. It's kind of double counting, but you know what I mean. And then tz, z bar squared. So oftentimes, papers on this subject are called TBar by some abuse of notation because of the first term. So this is the combination that we're studying. But we're now at separated points. I'm not trying to define a composite operator yet. It's all at separated points. And OK, and let me show you that this is true. I'll first show you a not a very insightful derivation. So for example, we could take these epsilon tensors and act on, let's say, well, let's act on this guy. Let's just see that this tensor structure disappears. And then you can, at home, work out the other tensor structures. So, well, so we just act on q mu, q nu minus q squared eta mu nu. And then q rho, q sigma minus q squared eta rho sigma. So that's what we need to compute. So there is this piece that comes from multiplying this and that. This immediately disappears because of the anti-symmetry of the epsilon tensors. So there are only 3 pieces left. So the first piece is epsilon mu rho epsilon nu sigma q mu q nu q squared eta rho sigma. That comes with a minus sign. Then there is a similar piece that would give the same contribution at the end. There is a similar piece. And then there is the piece that looks like plus q to the power 4 epsilon mu rho epsilon nu sigma eta mu nu eta rho sigma. Okay, so now how do you see that this vanishes? Well, an important little observation a convenient trick is to define in 2 dimensions. You can define like a dual pseudo vector, if you like, in this fashion. So you can just define a dual vector, and you can check that it satisfies the property that q twiddle squared is the same as q squared. Okay. So with this little trick, you can check. Well, this gives you q twiddle. This is another q twiddle. Then they're dotted into the eta symbol, and you get q twiddle squared. But q twiddle squared is the same as q squared. So you have q to the 4. And there is a q to the 4 from here. So the first 2 pieces give you 2 times with a minus sign q to the 4. And that's it. Now the second piece gives q to the 4 times this. But this is the determinant of the eta symbol times 2. So this is 2 times the determinant of the eta symbol, and this exactly vanishes. Okay. So, and by in a similar fashion, you can do the other tensor structures. Okay, so there is this funny property that we learned, which is that this is a very strange thing a priori. So we just learned that epsilon mu rho, epsilon nu sigma, t mu nu x, t, this is still in R2. We're still in R2. We see that this is independent of the distance. Okay. So this this two-point function is entirely, it's like topological, even though the theory that we started from is massive. This two-point function will turn out to be like a topological thing. So it doesn't, this is somewhat strange because without supersymmetry, without integrability, it's somewhat strange that there exist such two-point functions. But yeah, apparently they exist. And now we'll try to see what are the consequences. What are the consequences of that? Are there any questions so far? Okay, so while it's independent of x minus y, you could imagine taking x and y to be very far from each other using cluster decomposition, and then this would reduce to the product of one-point functions. So since it's independent of x minus y, we can just take x minus y to infinity, and then this is the same as tt with the appropriate indices.
Why is it dot 0? Show that the Fourier transform was 0, right?
Just a second. I'll just put the indices. Yes, what's the question?
The Fourier transform was 0.
The Fourier transform was 0.
Now you're saying it's independent. Why isn't it just 0?
Yes, it's a good question. Here I was Fourier transforming the connected two-point function. This is why it's I don't have like double delta functions. And here I'm saying that if you look at the connected one, it would be 0. So the connected is 0. But if you look at the disconnected one, it could have this piece. So this is the general two-point function. And here maybe I should have put a small superscript like C, 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 C. Okay. Would that be okay? That would be okay? Okay. So what are the consequences of this fact? So the first consequence that I would like to emphasize is for the operator product expansion. Suppose I bring two t's very close to each other. So it's not true that if I inserted more operators here, it would be independent of the distance. It's something that's true in the vacuum. So, but that already has some interesting implications for the OPE. So what do we know about the OPE upon constructing this with the appropriate epsilon tensors? So what this fact implies is that there is some composite operator, perhaps, and that's what people define as TBar. Let's put it at 0 so that we don't have too many symbols to carry around. So the first piece is some composite operator. And this is fine. So the VEV of this composite operator on R2 would have to agree with the product of the one-point functions. So this composite operator in flat space behaves like a Landau-Ginzburg field. It's a one-point function, just factorizes. So here we've done the computation of the two-point function in flat space. We've seen rigorously that is the product of one-point functions. And we can just call the first piece in the OPE. There is a regular piece in the OPE. And that regular piece is defined to be TBar. So that bar here doesn't mean anything. It's just a symbol for a new composite operator, TBar. Okay? It's not, this is just a symbol. So we see that it behaves like a Landau-Ginzburg field in flat space in any massive QFT. But then there could be more pieces here. There could be more pieces here because we don't know what happens a priori when we have more operators inserted. But the deep thing that this implies is that these pieces are derivatives of stuff. so that when you study this when you study the 2-point function in the vacuum, it disappears because of translational symmetry. Okay, so there could be lots of operators here, and well, we don't know what they are in fact, but we know that they are total derivatives. So those of you who have ever looked at supersymmetry, I mean, very similar to the kind of stuff that Leonardo and Chris are doing. This is very similar, right, Leonardo? Would you agree? Where is Leonardo? It's very similar. It's like saying that there's this plus Q exact stuff. But here there isn't supersymmetry. So that's the nice thing. Say again?
Do you only make derivatives so that the one-line functions in the vacuum manage?
Yes.
So what if it happens to be conformal theory and then there's not another selection which says that unless given dimension is zero, then the line.
Right, but this is like in a general massive QFT. You can easily rule that out. You can study the consequences of the word identities when additional operators are inserted, and you can just show mathematically. In fact, I'll show it soon, that all the correlation functions will have factors of momentum in front of them. So you can really prove that this is correct. Okay, so this is this shows that this operator TBar. This is kind of elementary, but now the idea is that we deform by TBar. And why do we want to deform by TBar? So we learned that in flat space, TBar behaves almost like a Landau-Ginzburg field. So it might be, so the idea is that since it behaves almost like a Landau-Ginzburg field in flat space, deforming by it might lead to a simple theory, even though if you write it in components, like if
What's Landau-Ginzburg field?
a Landau-Ginzburg field is a classical field.
Free field.
Yeah, classical statistics. Yeah. Yeah. So TBar seems to behave like a classical field. Maybe I should say classical rather than Landau-Ginzburg. And so deforming by it might lead to some simplifications, even though if you write it in terms of the elementary fields of the theory, it would seem like a horribly complicated interacting system. So the idea is that we add to the action some coefficient alpha times TBar x, and we integrate it over x. And what comes next is like utilizing this fact about TBar in flat space, and then studying it also in compact space, and using these simplifications that TBar enjoys to compute partition functions, energy levels, many things in quantum field theory, even without, as I said, supersymmetry. Alpha is the coupling constant. So you can think about it as 1 over the cutoff squared. Okay. But I'll just write it as alpha because soon there will be derivatives and it would be inconvenient to keep track of this kind of thing. So I'll just write alpha. Okay, so so the idea is to try to see where does that lead, given that TBar seems like a relatively simple operator. Good. So ordinarily, when we take two operators and we want to define a composite operator, we should worry about singular terms, and then we should throw them away. And if there are logarithms, then we're in bad shape. But in principle, you throw away the singular terms, and that defines the composite operator. Here, there cannot be singular terms, because you're only allowed to have derivatives of stuff. And you can convince yourself by dimensional analysis that there isn't any candidate for a singular term just by dimensional analysis. So the fact of the matter is that there isn't, but even if there were, it wouldn't matter, because you can always define composite operators by throwing away the singular terms. So TBar as an operator is defined by the limiting procedure of x going to 0, these two epsilons, Tx, Ty. Oh, sorry, T0. That's how we define it, where the limit is taken by throwing singular pieces, but the fact of the matter is that they don't exist in this particular case, so we don't even care. Great question. It will come soon. Yes. This will be, OK. So before we try, so let's just discuss what does that do in flat space. Well, in flat space, as we've argued, there is exact factorization of this two-point function. Oh, sorry, this operator behaves like a product, so it's rather easy to solve the theory. But you don't learn much from it. Suppose you want to understand what happens to the energy levels of the theory on a circle, which is a slightly more physical and straightforward observable. So the first thing that I want to discuss before we try to solve this model is what happens on T2.
What's the definition of the model?
The model is given by some QFT, which already has some massive parameters, M1, M2, blah, blah. And now you add alpha. And suppose you solve the model where alpha was vanishing.
But does it define the model?
Yes. And so suppose you have.
In other terms, is there like alpha squared something? Because if there's one irrelevant deformation in the infrared, there are going to be probably many others.
No, I'm not thinking about RG flow. We don't do RG flow. This is exact.
That's why I asked if it defines the model.
Yes. So, OK, let me just try to give a picture that could be useful. So we're doing we have some QFT that exists at alpha equals 0. The QFT gives some energy spectrum. And now we add some irrelevant term with some finite coefficient measured in the units of the already existing masses. So that defines the theory.
It's not clear to me that it defines it.
Well, it could be a sick theory. It could have ghosts, but it defines the theory.
I don't think it defines it. The reason why I'm asking is that because you said that you're going to present it in a way more clear than other presentations.
So there is.
I think it's at the same level.
So this is alpha. Alpha is like a parameter in the space of theories. And RG flows go in this direction. RG flows have nothing to do with alpha. So for each alpha defines a theory, and then there is an RG flow.
But to define the theory, you have to give something more than just write this equation.
Well, I'll define it in an algebraic way. This is just a picture. I'll write well-defined equations that would tell you what it means to do that. And that defines the theory. But that's just a picture. But you don't have to confuse alpha with the RG flow. There could be many massive parameters, and the RG flow would change all of them. But you could also change alpha independently, measured in units of this, measured in the units of those massive parameters. It's like imagine in the standard model you could add some operator of dimension 6. Its coefficient could be 1 over TeV.
But precisely, the standard model would not define the theory.
Well, you could say, let's add an operator that is irrelevant to the standard model at this scale, and we try to compute the energy levels on some compact space.
But only energies below that? Only
Yes,
below.
yes,
Okay,
suppose.
that's fine.
But you would not be able to compute them with different precision. This would be just a computation valid to first order.
Right. Right. You could make further assumptions saying that, let's say that this is the only operator that exists.
But that would be a very weird assumption for the standard.
Right.
model.
Right.
Definitely wrong.
Right. So the magic here is not that we need to make this assumption. The magic here is that suppose you already have a full theory, and you just ask how do the energy levels depend on changing alpha.
And it's a circular argument. Anyway, I don't.
No, it's not a circular argument.
But the standard model would be circular.
No, it's not. But it won't be important. I'll give a different definition. This is just maybe an intuitive definition, if you like. So this is the RG trajectories, and this is the alpha trajectory. They have nothing to do with each other. Alpha defines the theory, and the RG evolution changes all the parameters simultaneously. OK. So we have to do some analysis on T2 before we can maybe give a more algebraic definition, like Flava wanted. So this is T2. So mu rho. So now I want to show you a little bit what happens on T2. On T2, the computation is not as simple as what we've done before. because there isn't Lorentz invariance. There isn't rotational invariance. T2 just has 2 isometries rather than 3, so the correlation function is not as constrained. But it will be important to get some to go through that exercise, because the key to what happens to the energy levels and when we add this deformation is in studying this 2-point function on T2. So there is here a very cute trick, which is the following. So we have some suspicion that perhaps the dependence on x minus y is very weak. So we take a derivative with respect to x in some direction alpha. So the derivatives are going to be with respect to x first in the direction alpha. And alpha has nothing to do with the indices that are already constructed. Okay, so that's what we want to study. And to study that, we can't use the conservation equation right away because the index is not constructed. But there is a very deep identity in 2 dimensions that I'm going to utilize in order to simplify this computation. Okay, this is a deep identity that's true for any 3 indices acting on anything you want. And it's true in 2 dimensions. You can just plug indices and you'll see that it always reduces to some tautology, this combination. So using that identity, we can rewrite this object in terms of, so we just reshuffle these indices, and then we get a d rho x, and then epsilon. Let me put the alpha upstairs. That would be much more convenient. So we have d rho epsilon alpha mu, epsilon mu sigma, and the same thing. And then we have another piece, which is dx, and now d mu, epsilon rho alpha mu sigma, the same thing. But now the 2 indices are constructed. You see, this mu index is now constructed with that, and the rho index is constructed with that. So now we have to use an important fact about T2, that it's a homogeneous space, and correlation functions still depend on only distances. And therefore, the 2 pieces vanish at x not equal to y. So here we used, very importantly, the fact that it's a homogeneous space, that the correlation function depends only on x minus y. And so the generalization to non-homogeneous spaces is difficult. But for homogeneous spaces, we can arrive at that conclusion at relative ease. But now there is no.
But the second term vanishes always by conservation.
Not always, only at separated points. But yes, it vanishes always. The first term is the one that you cannot simplify if the space is not homogeneous. Because in the first term you have an x derivative, but it's constructed with the energy momentum tensor that's sitting at y. Yes, so you need to transfer it to the other one by using the fact that it's only a function of x minus y, and that's impossible in general spaces. So you have to do something more. So what do we learn about this correlation function on T2? So we don't on T2. The amusing thing is that there isn't any cluster decomposition anymore because you cannot take the points to be arbitrarily far away. Yet we have shown that it's independent of the distance. Okay. So what do we do with that guy? It's not correct in general that this is going to be equal to Tx on T2 times T0 at T2. So that's not correct anymore. There is no argument of why it should be true. So the correlation function may have a connected and a disconnected piece, unlike in flat space. And the connected piece is very important. But it is still true that it's independent of x and 0. So there is the following trick. When I write this thing, I always mean the combination with the epsilon tensors and the indices. Okay? So even at separated points, when I write TBar, I mean T mu nu, T rho sigma with the epsilon tensors. So there is the following trick. You could say, okay, we cannot factorize the correlation function, so it's not as easy as flat space. but we can still average over x. So we can say, let's integrate over x, divide by the volume of T2. Okay? And then we have a 2-point function, but now essentially at 0 momentum. That follows from the fact that it's independent of the distance. We can just average over all the points. And here there is the issue that somebody already asked me about, contact terms. So when you average, you might be worried because in all of these derivations before, we've shown that it's independent of the distance at separated points. And typically there are some delta functions. So you need to worry about delta functions. And in fact, so you have to add some contact terms. These delta functions can be fixed, but I don't have time to explain how. You just need to subtract them by hand for this formula to be correct. Otherwise, you pick up some wrong delta functions. Yep.
Sorry, now we have x expressed in the left-hand side.
Oh, I'm sorry. Well, but it's still correct, though. Even I could put x prime, it would still be correct. Is that okay? You see why? Or, yeah?
Because it's independent of.
Yes, it's independent of x. So. Yeah. Okay, so this could have been a separate topic I could explain, but I'm not going to go into that. It's a little bit technical. So now what's next? So let's suppose that we understand these contact terms in complete detail. We don't talk about them anymore. And we'll just be a little bit more schematic. I'll incorporate the effects of these contact terms when needed. What is this thing? This is the 0 momentum 2-point function on the torus. And this has a nice representation in terms of derivatives of the partition function with respect to geometry. So the first piece can be written as the second derivative of the partition function with respect to various geometric deformations of the space. So we can write it as dg, let's say alpha beta, dg gamma delta, and then put epsilon alpha gamma, epsilon beta delta. So that's the first piece. And the metric variations that we do here are just overall metric variations, not local metric variations, but just overall variations of the torus size, the torus sides, the lengths of the various torus parameters. So these are like zero mode metric variations of the torus. Is that clear? So we change the sizes of the torus, the angle between the two, defining unit vector, cell vectors, and so on. And the thing is that after working a lot on these contact terms, what you find is that the piece that you need to add is very simple. So to account for these contact terms correctly, you need to add the following piece: g alpha beta, dz, dg alpha beta. And that's it. So this is the fact that I cannot explain here of where this comes from because it's too technical. But at the end, you find the following equation. Yes? Say again? Yes. Sorry. Yes. Thank you. So we find the following equation, and this equation is valid on any homogeneous space. We find that if we take a derivative of the partition function with respect to alpha, that's the same as the 1-point function TBar on this homogeneous space. You can think about the torus. So that's the same as, according to that logic, as 2 times over the square root of the metric. I'm imagining a torus here just for simplicity. So the square root of this is just the area of the torus. Okay. And then we have parentheses, the area of the torus squared, then epsilon I k epsilon jl, the second derivative of the partition function, dg ij, and then dg kl. And then there is this piece that I did not explain that comes from the contact terms. So this is the equation. Alpha is the coefficient of TBar. This is the 1-point function of TBar, if you want. Who asked this question? Oh. This is the one-point function TBar, which you can just define as the derivative of the partition function with respect to the coefficient. This is not an RG equation. The RG equation is the Kalan-Zimanski equation, and it would depend on other massive parameters that exist in the theory. This just says how does the theory respond to just changing the coefficient of one irrelevant operator by a tiny bit. It's a completely well-defined problem, in my view.
It's a defined problem, but I don't agree with interpreting it as a definition of partition function of a theory, which we have another definition for. In the sense,
That's fine.
Definition.
That's the definition. We can accept that. I'm happy to accept that. What is the physical meaning of that is that you have a theory. It has infinitely many relevant operators, many relevant operators. And this just says how the partition function responds to changing the coefficient of one irrelevant operator by a tiny bit. That's it. This is not an RG equation. And this is a point that also took me some time to realize, so I'm emphasizing it. OK. Now, we want to write it in terms of variables that are more natural for the torus. These variations with respect to the total metric components doesn't have a very clear meaning, right? I mean, we don't know what it means intuitively. So we need to do some changes of variables and transform to variables that are more akin to our intuition. So we take the torus to be like a parallelogram, like that. OK. So this is our torus. Now, let me put the coordinates. So I'm going to rewrite this. This is like a morass of chain rules. Now, you have to go from these variables to the normal variables that we like on the torus. So this coordinate here would be x2. This is x1. And this coordinate here is going to be y2. So I'm using very old-fashioned notation. X is the x-axis, y is the y-axis, and these are the projections of this vector on x and y. And then there is x1. x1 is the length of the circle. So now you need to do a change of variables between these variables and these variables. And this is, well, it's just a long technical exercise. Let me just tell you the answer. You can take it as a small homework problem to do it. Like 1 page of algebra. Well, by the way, you could also do S2. S2 would be a little different. You can so you can view this equation, Slava, you can view this equation as a flow in the space of theories, not RG flow. This is just a definition of a flow in the space of theories, but not RG flow. So, OK. Let me just do this change of variables now. So we find that dz over d alpha equals d1 hat. These are two differential operators that pop out from the change of variables here. And I'll just give you the explicit expressions for these differential operators, which you can also then play with. So the first one is y2 over x1. Sorry, the first one is going to be d squared over d x1 dy2 minus y2 over x1 d squared over d x2 squared plus x2 over x1 d squared over d x2 dy2 and 1 over x1 d over dy2. And the second one, I'm just giving you the explicit expression so that you could verify at home or play with these equations if you like. Then there is x1 d over dx1, x2 d over dx2, and y2 over d over dy2. So these are the two differential operators that you will encounter if you do this change of variables carefully. OK, so Now we're ready to find what are the consequences of this irrelevant deformation. What happens if we change this irrelevant coefficient continuously? What happens to the energies and so on? So for that, we need some convenient representation of the partition function. Now that's familiar from conformal field theory. You've seen such expressions before. We need a convenient representation of the left-hand side of this equation. This is the defining equation, so in some sense. Okay, this is the most important equation from which everything follows. So now we need a convenient representation of the partition function on the torus, so that we already have a nice representation of the right-hand side. Now we just need some convenient representation of the left-hand side. So here we just think about it as a thermal state. Okay, as usual. The temperature is being Y2. And the momentum is coupled to X2. And X1 is the size of space. So therefore, we just get e to the minus the energy levels as a function of the size of space. The energy levels are always just functions of the size of space, multiplying Y2. And then we have I. And then there is the momentum. And then there is X1. X2, sorry, yes. And now, it's important to remember that the momentum is not really a function, a non-trivial function of X1. By quantization, it has to be an integer over X1. So if you change this coefficient of the irrelevant term TBar, it's not going to affect Pn. So Pn is not a function of alpha. However, this is a function of alpha. I should have put an alpha here. The energies are a function of this irrelevant perturbation, but not the momentum because it's quantized. So the momentum will just come along for the ride. So now you see what happens. On the one hand, we have some derivatives with respect to the geometry. X2, X1, 2, Y2, X1. And on the left-hand side, we have a derivative with respect to alpha, so we can directly hit the energy levels. Okay? So we get differential equations for the energy levels as a function of this irrelevant coefficient. And here, one needs to do quite a bit of algebra, because these differential operators are complicated. And you need to act with them correctly, not make mistakes. And what you end up finding after you do this algebra, this is an exercise to verify. You find that each energy level obeys its own equation. So they don't mix. Unlike what you might have thought, and what you might have expected from experience in higher dimensional theories, the different energy levels don't mix, and each obeys its own equation when you do this irrelevant perturbation. And the equation is the following. And then there is one more piece, which is ln squared over x1 cubed. And there is some 4 pi somewhere, 4 pi squared. There is a 4 pi squared here. So that's what you find. So surprisingly enough, and this is probably characteristic of 2 dimensions, you can define a consistent theory by changing this irrelevant operator, only the energy levels change independently of each other. That's probably inconsistent in higher dimensions.
Does this follow from the equation on the left board?
Say again?
Is it the equation on the left board or something else?
Yeah, I'm just saying everything follows from this equation. So the left-hand side literally leads to dEn over d alpha, because that's what happens when you hit this with d alpha. And the right-hand side leads to a morass of derivatives with respect to x1, x2, y1 that you need to work out, and it collapses to this nice equation. Okay. So everything follows just from this. I didn't make any other assumptions. I just used the conservation equation, and that's it. Yes?
Is this equation the same that you get in flat space? Yeah. Like in cylinder?
This is an equation for the energy levels. So if you're on an infinite cylinder, you can study what happens on an infinite cylinder in some energy eigenstate, or you can just study it in the vacuum. This is an equation for the energy levels on the cylinder, and we've obtained that by putting the theory in a circle in a thermal state, and then applying this differential operator.
If you don't include that contact term, you know what you get.
Well, this is the contact term.
Right.
Well, yeah. If you don't include that piece, you get nonsense. You get some equation that is just nonsense. It doesn't even have. It doesn't have reasonable scaling. Yeah. So it's important to include that piece, otherwise you get nonsense.
The fact that you could get stress tensor insertions from just global geometry of the torus, that was a very two-dimensional thing. Is that where the 2D thing is?
No. The 2D comes in.
Usually I do metric variations that are local to get stress tensors.
Right. Usually, so the energy momentum tensor is defined, right? The energy momentum tensor is usually defined in terms of variations of the partition function with respect to the metric, right? Up to some square root of g is here. That's how it's usually defined. What's the magic here? The magic here is that we've defined a composite operator. That's basically, you can think about it as t squared, okay? We added it to, we ask what happens if we change the coefficient of that operator in the action, okay? And the magic is that we were able to reduce that to a second derivative of the partition function with respect to constant modes of the metric. Constant modes, that's the key. Just rescaling of the torus. So the torus remains flat, but we're rescaling its sizes.
So what's breaking in higher dimensions?
In higher dimensions, this would not hold because you can still define this composite operator by a limiting procedure, but there is no independence of the distance. And therefore, you cannot rewrite the appropriate second derivative in terms of derivative with respect to constant modes. You'll have to write it as a second derivative with respect to some position-dependent variations of the metric, and there won't be any way to make progress because there won't be like an independent presentation of the partition function that's useful. So the key is that there is this topological sector, that the position is immaterial, and that's why you can rewrite a short distance thing where you collapse two energy momentum tensors to the same point in terms of an integral over the whole space. Okay? Or in other words, the OP in higher dimensions is not as simple. I wrote the OP at some point here. The OP is not as simple. It's not just TBar plus derivatives. It's just not as simple. And presumably there doesn't exist a combination of T's in higher dimensions without additional assumptions that obeys such an OP. Okay?
What do you actually mean in higher dimensions? I mean, the epsilon tensor will have more indices.
Yeah, first of all, you don't have the epsilon tensor. You need more indices. It's unclear if how to do it in higher dimension. Okay, so
Does it matter if there are generacies?
that the energy levels don't mix? It's a good question. No, the answer is that it doesn't matter. It doesn't matter. It's a good question, but the answer is that it won't matter. Yeah.
So remember, Cardi has a paper that he hasn't this contact term, and
Yeah, so there were some, I didn't mention the literature, but indeed, there was some paper of Cardi where he got the wrong equation with the wrong proof, and then there was a second it's a mess. Yeah, it's a mess. There was a wrong equation and the wrong proof, and then he just observed that you don't get the right answer if you use the wrong equation. Then he added another term to fix the answer, but the proof is still wrong, and it's kind of a mess. I just try to give you a streamlined point of view.
Sorry, just to streamline a little bit. Do you agree that this equation for the energies, that's the only valid definition of this theory that appears so far?
What is
I think that this equation...
this one is more general.
But this is a very bad equation. Look, it is a diffusion equation where the high derivative term is not elliptic. So it's not what? It's not elliptic. Yeah, look there, because dx dy.
Yes.
You know,
Yes.
squared minus dx. It's a very bad equation. And unless you plug in z in the form that you wrote for the partition function, solutions, I don't know, maybe you studied them, maybe you know how to...
No, there are solutions also in other cases.
But solutions are terrible, you agree. So this equation, I'm not sure in which sense it is a well-defined
This
mathematical equation.
I agree. This equation is correct. And you can, on the torus, it simplifies to what we just found. But it also can be solved on other spaces. We have solved it also on other spaces. And it does lead to a sensible, on other homogeneous spaces. And
For example, what?
a sphere. And it does lead to consistent solutions. These derivatives here are just with respect to the zero modes. And these zero modes don't even exist on generic spaces. And you might remember that in deriving these equations, I assumed that the space is homogeneous. You remember that? Because I assumed that the correlation function depends just on the distance.
I remember that, but yeah, but I'm looking forward to see how you solve this on a sphere or something for which you didn't know the answer. No, I'm not trying to be saying. It just seems to me that at least on a torus, this energy definition is much better definition of the theory than.
Right.
Because this is a well-defined equation.
Yes.
Right? There is no problem. But the left-hand side needs some additional. The thing on the left board definitely needs some additional.
Yes.
Words to say.
Well, for example, you can also accompany this equation with the idea that perhaps you don't want other irrelevant operators, but you just want one. That would mean that this trajectory has to be parallel to the alpha trajectory, and that can simplify the equation a little bit. But in general, I agree. This is not a complete definition of the theory.
I meant something more simple. You need some boundary conditions on, where the volume of your torus goes to zero. There is some terrible singularity in this equation, and because it's not elliptic, it's not clear what's coming from the singularity.
That's correct. I completely agree. And there are many open problems.
The paper of Cardiacal technical details, but it contained a very interesting physics point, which you completely neglected in your discussion. The theory, so you keep talking about the theory, but one thing which comes out very clear from Cardiac's paper is that this theory we are studying is not a quantum field theory. So he gives this physics picture for coupling QFT to a fluctuating metric and so on. So it's a theory for which the concept of UV completeness, with which we are familiar for QFTs, has to be completely revisited. And
right.
So it's also related to the work
right.
that Victor was doing.
Right. The questions of what is... I haven't got to that point yet. I'll get to this discussion soon. What I'm doing now, so far we have done three things. We studied rigorous properties of the energy momentum tensor correlators on the torus. This is always true. Then this equation follows. This is always true. This is just the one-point function on the torus in any massive QFT of the operator TBar. You can just check it in the tricritical flow. This equation holds. So everything I've done so far is absolutely rigorous. The point at which it's going to become murky is when we try to understand the properties of these solutions on small circles. We'll encounter some singularities, and then the UV. There are questions about the UV completion. But so far, I did something that is entirely rigorous.
But the moment you turn on alpha,
I'm not turning on alpha. No, Slava, you're confusing. Suppose you have an energy flow between two CFTs.
Is alpha infinitesimal or finite?
You can take this equation like this. Okay? This equation, alpha equals 0. Let me just explain again. Suppose you have a flow between two CFTs. Okay? It's a completely well-defined problem to ask, what is the expectation value of this operator at some, intermediate scale? It's a renormalized operator. You can ask, what is its one-point function in this flow? And let's say even on the torus. You can put this flow on the torus, and you can ask, what is the one-point function? It's a completely well-defined problem. It's UV complete. This is the answer. If you knew the partition function of the undeformed flow, you could compute these derivatives. You would extract the one-point function. This is already very, very non-trivial. We cannot do something like that in higher dimensions. We don't have because we cannot relate this one-point function of the composite operator to some global derivatives of the geometry. So that's always correct when we just put here alpha equals to 0. Okay? Now, the step at which it becomes a little bit more interesting is when we try to add alpha to this operator to the action. And then there are many interesting discussions that open up. But what I've presented is entirely rigorous and independent of that so far. Even that's the first thing that when we try to solve this equation, that's the first point where we try to go beyond the usual rules of quantum field theory and see what happens. Yeah.
So this may be asking
same thing in a different way. But,
Yeah.
If you define the theory by this change in energy levels,
Yeah.
right, then how do you know that theory is local?
Right, you don't know. And you don't know. One has to distinguish the things that are always true from the speculative direction in which I'm going to go now. The things that are always true are the properties of TBar that we've investigated. That there is this kind of, you can obtain the one-point function of this operator from the integrated two-point function. And that leads to this nice equation. That's always true. Now, when we try to solve this equation, not around infinitesimal alpha, we're going into some uncharted territory. We're trying to go into the UV, so to speak. We're not just studying correlation functions in well-defined RG flows. We're deforming the RG flow. We're deforming the theory and seeing where does it take us. Okay? So that's a more ambitious thing. But that's where I want to go now, to the more speculative direction. So this equation, as many of you know, has a name. It's called the Burger's equation. This is called the Burger's equation. So miraculously, this equation inviscid. This is the inviscid Burger's equation, meaning that it doesn't have viscosity. And this is a forcing term. So you can think about that. So okay, the analogy would be that alpha is like time, which we like. Rg is like time. Or you can think about this. OK, alpha is like time. X1 is like space. And it's indeed like space, also in our equation. And this is a force that depends on space. So this is a forced inviscid Burger's equation. And you can solve it by the method of characteristics. It's an integrable system. Let's just take the momentum to vanish. That's the first assumption. Let's assume that we're looking at the energy levels of some momentum zero eigenstate on the circle. And let's further assume that at alpha equals 0, we have a conformal field theory. OK, so then the energy level of the unperturbed system, the energy levels of the unperturbed system are going to be the usual expressions that you know from radial quantization. And that's going to be minus, and then pi over 6. And then the central charge minus 24 delta. Oh, I already put the 6. So this is the energy level of the unperturbed theory. And now we're doing something that's beyond just one-point functions in well-defined RG flows. We're starting from a CFT, adding this irrelevant operator with some coefficient, which is measured in the units of the size of the circle. And we ask, what are the energy levels? So we don't do RG flow. There is no RG flow here. We just, let's say that the circle has size 1 kilometer. So we add an irrelevant operator with coefficient 1 over 1 kilometer squared. Sorry, whatever, you know. So the coefficient alpha is defined in terms of the size of the circle. But we're not doing RG flows. OK, so you can solve this equation exactly. And you can find the answer. And the answer for the energy levels as a function of x1 and alpha is the following. So there is some piece that you can interpret as the renormalization of the cosmological constant. And then there is some piece that I'm going to write now carefully. So what is C? This is also defined as capital C. And you can check that when you plug out. OK, I didn't say what is alpha twiddle. Alpha twiddle is just a alpha. Well, so in my it will be, yeah, in this case, I can just replace it by alpha. So you can just check that at alpha equals 0, and f of alpha well, this is just a renormalization of the cosmological constant. You can ignore this piece. This is just an extensive contribution to the energy. And we can just ignore that. It won't be important for the forthcoming discussion.
Sorry, can I ask why is it a function of alpha? I mean, by dimensional analysis, alpha has dimension.
Yes, you're right. Yes. So here, when I wrote this equation at home, I also accounted for a possible tree-level cosmological constant that you just can't control. So therefore, this appeared. But let's just erase that. It won't be important. As you say, you can just remove it by a counter term. OK, so this is the answer. And C is this object.
In the first equation, you probably forgot to divide by x1.
Right. Right. Thank you. OK, so this is the answer. And now, OK, so now this is already slightly beyond the realm of ordinary QFT. But what are the lessons that we can learn from that? One lesson that is that's very evident is that, sorry, the chalks are just not working. What about this? OK. One lesson that's evident from here is that if alpha c is negative, so that's like saying that we're putting this irrelevant operator with a certain coefficient. This square root develops a certain branch singularity, and things become imaginary and break down for some sufficiently small circle size. So this theory seems to be genuinely sick in some sense. But so this is sick because on sufficiently small circles of the order of magnitude of this irrelevant perturbation, you lose control. Or the energies become imaginary. But if this is positive, everything seems to be fine. The energy levels are fine. And then people have found that you can find that there is some Hagedorn density of states. But I don't have a white chalk that works. Yeah, but they don't work. What about this? I still have 10 minutes. I wanted to explain the meaning of all that.
This fake chalk, perhaps. Does this work better?
OK, great. Thanks. OK, I'll just write it from the beginning. So we start from some, the picture is as before. Let me just draw the picture again. So alpha is the coefficient of this irrelevant operator measured in some units. Let's say the circle size or the mass scale of some already existing particle. So we start from some QFT here that we understand. Let's say a conformal field theory. And then we add this perturbation, and we ask what happens. So what we see from the previous analysis is that if alpha is positive, if alpha c is positive, then the energy levels seem to be fine. So here we get the sensible, at least sensible energy levels on the circle. While for the other sign, we find a certain square root singularity, algebraic singularity. That's familiar for those who ever looked at the Berger's equation, because this equation develops shocks with algebraic singularities. So there is a square root singularity here, and the energies become complex, and it's not very clear what to do with that. But here the theory seems to be somewhat well behaved. However, you can show that there is a Hagedorn density and therefore for sufficiently high temperatures, the thermal partition function would not quite exist. So you cannot bring the system into thermal equilibrium at sufficiently high temperatures. OK, so these are just facts.
This density of state should be continuously connected to the undeformed theory.
Correct, but when you crank up alpha, then you can imagine that the energies become a little bit denser, so that the energy density, the density of energy levels grows.
At a particular point in alpha?
Yeah, there is a Hagedorn density, which means that at sufficiently high temperatures, there will be a singularity. And this temperature could be of the order alpha, if I remember. Was it in the order alpha?
If you find a Hagedorn density, do you trust the Hagedorn density, or do you decide that this calculation didn't make any sense because you used the partition function?
Okay, so I wanted to split the discussion into two parallel tracks now. Can I? And then we'll discuss this. Yeah.
Does the sign of C depend on energy level?
Here?
So C is like, large C is C minus 24 delta. So it seems that you have delta which is 24.
Right, so for a, so in this convention, this is this head. Right, so capital C is positive for generic delta. Capital C is positive for generic delta. Generic large delta.
If you're talking about an entire theory, it has like all the states that it has.
I think the confusing thing is for either sign of alpha, there are some states
Yes.
which will become complex. So both theories have this square root problem. It's just for positive alpha, it's the negative energy states.
Right. So now I would like to split the discussion into two parallel tracks. Since obviously there is some speculative stuff going on, but there is also some rigorous stuff that's going on. And I just want to mention like what are the possible ideas of what this could mean. So one aspect of this discussion was the study of correlation functions of this sort in well-defined RG flows in quantum field theory, let's say on the torus or on the sphere, whatever. So this aspect, I think, is completely rigorous and well-defined, and there is a new observation here that there is a topological sector that's embedded in any QFT. So this is some sort of a topological sector. So you can do some computations exactly in arbitrary two-dimensional RG flows. That's the first aspect. The second aspect is adding this funny operator to the action. And then there's this picture that we're trying to define a space of theory. We're trying to enlarge the space of theories by adding this additional coefficient alpha. And here, the meaning of that is more speculative, obviously. We have to understand if this really defines a local quantum field theory, if changing alpha is a sensible thing to do.
Sorry, when you change alpha away from 0, if it's not a quantum field theory, then how do you know whether this TBar operator still exists?
No, that's why I'm making this distinction. Suppose you have a QFT, an RG flow from one fixed point to another fixed point. The first deep observation in this business is that there is this special correlation function that is independent of the distance. So in flat space, it's totally boring because you can just separate them very far apart and it factorizes. But on the torus, it's not. On the torus, you get some kind of interesting zero mode that you cannot get rid of. But if you know the partition function, for example, as a function of the torus size, which you do in many examples, you can compute this one-point function. And it's in any case, it's regardless somewhat interesting that there is such a topological sector in arbitrary RG flows in 1+1 dimensions. That's a new technical observation. That's correct. That part where you try to define a new theory by adding this to the action is more speculative. And there are many people who propose various ideas of what this could mean. Obviously, the theory has some sicknesses for either sign. Either most of the energy levels are negative, as imaginary, as Edgar said, or you get a Hagedorn density of states, and while the positive energies seem fine. Okay, so that's the part that many people are discussing in the literature now. This part is not very much discussed. The significance of this topological sector. So I just wanted to give some maybe references with the help of the audience. to what kind of things people have been suggesting. This is just a summary, to my understanding. So one suggestion has been that there is that this alpha deformation that this direction alpha has an interesting connection to has an interesting interpretation in ADS-CFT, whereby so in ADS-CFT there was in the context of ADS-CFT there was a suggestion that this coefficient alpha has something to do with going inside the ADS or going outside of the ADS, depending on the sign of alpha. So going outside of ADS sounds like bringing back the one that Maldacena dropped in his famous decoupling argument. So that's like going back to flat space, away from the D-branes. And that's like maybe more black hole physics. So that's one suggestion. I guess this was, maybe the people in the audience know the references. This goes to, I guess, Mezei, Verlinde, Kutasov, Givon, others, Tzchaki, more. Edgar, you know who?
Going in is Mezei, Verlinde, McGuff. Going out is Kutasov, Tzchaki, Givon.
Good, thank you. And then there is the work.
The Israeli group is not saying go back to flat space, go back to this linear dilaton theory, right?
Yeah. Well, but Edgar, for example, tries to go back to flat space.
Well, I mean, it's just going out.
Going out, yeah. So I'm just saying that this is one possible direction that people, I'm just giving a summary. I haven't contributed to any of that. I'm just giving you a quick summary of what that aspect of the problem might mean. So there is some discussion going on in ADS-CFT. And then there is also the work that Victor and Sergey and others were doing, where I guess it would be fair to summarize that you are suggesting that the UV completion is actually two-dimensional gravity. So the UV completion for this, right? You don't have a suggestion for the other one.
For the others, well, my personal point of view that there is one sign of alpha that's definitely preferred, which is for one sign you always get finitely many energies that have complex energy, and for the other sign you get infinitely many levels which get complex energy.
Yeah.
I like the sign that for which you get finitely many. But there is another way, because if you do if your theory also, especially if it's a massive theory that allows to do scattering, so there is also the...
Yeah, let me just mention that for a second. I'll just mention this for a second. So in flat space, as I mentioned, correlation functions of this TBar are kind of boring because you can separate them to infinity. But suppose that we're in flat space. So this is like a picture of flat space. But you have a non-trivial in state and a non-trivial out state. So you have a scattering process going on. Then this argument that you can separate T from T-bar is still true in the bulk. But when you hit infinity, you pick up some phases because you would change the S matrix in some way. And it's very plausible, although there isn't a rigorous proof. There is almost a rigorous proof, but there isn't quite a proof yet. It's very plausible that this T-bar deformation also affects the S matrix in flat space by adding this prefactor, the famous CDD factor. So the S matrix of the original theory is deformed by adding some prefactor like that. Okay, and you can check that this leads to a unitary S matrix, and it's very nice. So this is another direction in which you could try to generalize this whole discussion. You could try to understand what happens with TT-bar in flat space when you hit the in and out states. And presumably that's what happens, although there isn't a rigorous proof. And if so, the S matrix in flat space seems fine. And you can think about it as the S matrix of quantum gravity. So this could be the S matrix of some quantum field theory, but this would be the S matrix of 2D gravity. It has it looks like it has the physics of black holes and stuff. Is this fair?
Yeah, I don't know what's rigorous, what's not rigorous.
Yes.
I'd say there is a proof, but I don't think it's rigorous. And there are some.
Okay, but this fact is, this is probably true. That also in flat space, you could try to understand the consequences of translational invariance and these conservation equations when you have a non-trivial in and out state. So obviously, there are interesting questions about entanglement. I'm going to finish in a second. There are interesting questions about entanglement. We've discussed the torus, but we've not discussed what happens when the torus has a branch cut. We haven't discussed the sphere. We haven't discussed the branch sphere. All those questions could be interesting. And also boundary CFT is an interesting way. A boundary CFT is an interesting playground to try to understand what it means. Because again, there is this independence of the distance, so you can imagine bringing the T all the way to the boundary and acting on the boundary. So it could be somewhat similar to that in spirit. So okay, these are various directions that finish my talk. Thanks. Somebody wants to make a comment? Or? I have not derived it. I haven't shown you why it's true. What I've shown you is, I mean, I've given you enough that you can do it at home easily now. You can start from this equation. You can derive the energy levels, and you can derive the Hagedorn density. It's just.
But you don't have to spoil it if you don't want to. But do you need the fact that the original CFT has a Hagedorn behavior at large? Or sorry, a Cardi?
Well, yes. You need to know. Yeah, it's important. An important input is what is the density of states at alpha equals 0.
Yeah. So in principle, if you started with a more general QFT, where the density of states was milder, could you avoid the Hagedorn?
Yeah, I think, yeah. I mean, yeah, definitely. If the original system like had finitely many energy levels, yeah, of course.
But for any QFT, you're going to land on this Hagedorn.
Yes, but I think for QFTs, you're bound to reach Hagedorn, because for sufficiently high temperatures, you can always think about it as a CFT in the UV in ordinary QFTs, and therefore the density of states follows, and therefore you'll get a Hagedorn density eventually. A Hagedorn temperature, I mean. Yes. Any other questions before we?
Can one say anything about the deformation of correlation function?
Yeah, that's another interesting. I don't think much was done in that direction, but well, it's somewhat like this. It's very similar to having some.
But this topological sector is restricted to be a statement just about the 2-point function, right? And doesn't go towards an operator statement.
Right, but you know that the corrections to the OP are total derivatives, so you might be able to utilize it in some way. For example, for the in and out states, you basically plug these derivatives, you go to the out states, you do a little bit of algebra, and you can get this factor just from the total derivatives. So it might be possible for some interesting initial states or interesting insertions. Like in energy eigenstates, it's very easy. You can just hit the energy eigenstate and you pick up what you pick up. So there could be some interesting states or correlation functions that you can solve. Yeah. Yeah, of course, you can ask, are there any other topological sectors? And the answer is yes. If you have, for example, conserved currents, you can define a similar objects. So for Kac-Moody algebras, for ordinary conserved symmetries. Obvious open question is if there is something like that in higher dimensions. Yeah, exactly.